So this interval tree consists of root, okay, v storing x mid, okay, and also the set I mid, okay, will be stored twice. Once in the list L left v that is sorted on the left endpoints of the interval, and once in the list L right v, which is sorted on the right endpoints of the interval, okay, and the left subtree of v will contain the interval. It's also an interval tree for the set I left. The right subtree will be also an interval tree for the set I right. Okay, and this interval tree on a set of n intervals use linear storage and has depths big O log n. Okay, so for the depths, this should be very obvious, right? Because each time, okay, you are going to break the set of interval at least. I mean, what should I say? Because you are finding the median of the endpoints. So at the most, you are breaking the endpoints. I mean, on average, you are breaking the endpoints like on two sets. Okay, and we don't even account for the intervals. That will be kept in the root. So the depths, this log n should be very obvious. Okay, but how about the linear storage? Okay, think about this. Okay, this argument is just like what we discussed. For each interval, okay, it must be stored in an internal node. Okay, and in that internal node, okay, it will only be stored in one internal node first, and that internal node, yes, it will store that interval in 2 copies, right? But that's it, right? Just 2 copies, right? So basically, like if you have n intervals, then the storage will be at most 2n, and even if you include the nodes required for the tree, okay, the total number of the nodes for the tree again will be linear too. So so the total storage space is linear. Okay. So this is the interval tree construction algorithm. Obviously, you can imagine this is the recursive algorithm, because you can see we call the construct interval tree, for the left subtree and the right subtree. Okay, so this is a very elegant algorithm. Okay, and as I already mentioned, like the depths as well as the storage space are really like inexpensive. Okay, and for the query, it is also very easy. Okay, because now, okay, the input will be one query point, right? Even though it's conceptually it's a vertical line, vertical straight line, but we only need to consider that particular x coordinate value, so it's a query point. Okay, so we have the root, we have root v of the internal interval tree, and the query point qx. That will be our input. So output will be all the intervals that contain qx. Okay, so basically, okay, you first compare the qx with the x mid. Okay, all that will be stored in the root, and based on the result, okay, you know exactly one subtree to get rid of, right? So if qx is smaller than x mid, then you don't need to worry about the right subtree, right? If qx is greater than x mid, you don't need to worry about left subtree. Okay, and if qx equal to x mid, then you only need to report all the intervals stored in the root, That's it. Okay? And say if qx smaller than x meet, as I say, like we don't need to worry about the right subtree, but we do need to deal with like the interval in the root, okay, as well as like the left subtree. For the left subtree, we just use the recursive call to query the left subtree. Okay, you don't need to worry about that left subtree stuff further. But for the interval in the root, okay, so basically walk along the list L left, okay, starting at the interval with the leftmost endpoint, okay, and if that left endpoint is smaller or equal to qx, we report it, okay, and then the next one, if it's still smaller or equal to qx, we report it. If we hit an interval that is greater than qx, then we just stop. We don't need to deal with the rest of them. Okay, so this is for the L left. If it's like qx greater than x meet, I mean we do the other case. I mean then we need to deal with L right. Okay, so basically that's pretty much about it. And this complexity interval tree for a set I of n interval uses linear storage, can be built in big O n log n time. Okay, using the interval tree, we can report intervals that contain a query point, okay, in big O log n plus k time. So this also answers, the question that we raised, at the beginning, okay, because if you try to compare every interval with this query point, then the complexity will be linear. So this one is obviously much cheaper than linear, right? And also this is like a output sensitive algorithm because this is plus k, where k is the number of reported intervals. Okay. So which is good, but there's a problem. Okay, these few slides, may be different from the ones in the handout, but I try to change that. Because I think that it will be easier for me to explain. Okay, so basically, okay, we originally we simplify the problem, right? Remember, we simplify the problem. Okay, we originally what we want to do? We want to do window query, right? And then we simplify the problem so that it becomes one-dimensional. Remember that? Okay, but now, okay, that one, the interval tree can be used to deal with that simplified version of the problem very well, but the issue is, well, at the end we still need to come back to deal with the window query, right? Okay, so window query is still different from the simplified problem, right? Okay, what's the difference? Okay, it's not sufficient that its left endpoint lies to the left of Q. In the I meet, okay, if say like when you compare the left the I left, when you compare L left, when you compare the L left, so if its left endpoint lies to the left of Q, then okay, in a one-dimensional, in a simplified case, we just report that interval, right? Okay, but okay, it is also required that its y coordinate lies in the range of qy prime. Because after all, we are talking about window query, right? There's certain y coordinate range we need to consider, right? For example, okay, so this is like a original say this is like the query window, the height of the query window, the height of the query window, and then well, let's consider this as like the, what should I say, the one of the boundary, the left boundary of the query window, and you can see that, okay, there's the range for the y coordinate, right? And so you can see that, for example, this particular segment S, obviously, if you consider this one as this Q as one-dimensional case, I mean, in that case, it's a straight line, right? So then you need to report this segment. But in this case, I mean, well, it has a range, okay? Y coordinate has a range. But unfortunately, this segment does not fall into that range. So this segment, even though its x range obviously intersect, I mean, it contains the Q, the x coordinate of Q, but we shouldn't report this segment because this segment is just not intersect, I mean, with this query line, okay? So we need to store the endpoint in the order list. Okay, I mean, originally we store the endpoint in the order list. Okay, it's not enough. Okay, it's not enough. I mean, when I say it's not enough, I mean it's not enough for the window query. Okay, so what do we do? What we need to consider is something like this. So it's an arbitrary x coordinate value. That's correct. But we have a range of y coordinates. Okay, so it's going to be, we don't care about the left space. Okay, because like what should I say? Like it could go, as far as possible. We don't care because what we care about is like if a point is on the left side of this particular query segment. But I mean, this query segment, okay, you can see there's a range for y coordinate. Okay, so we call that the qy prime. Okay, so say if these are the x meet, if these segments are the x meet. So now, what we are trying to do is what? Think about this. Okay, when you need to check this one, your Q, the x coordinate of the Q, the x coordinate is smaller than x meet, right? Right? Originally, in a previous solution, we store the left endpoint in increasing order, right? That's how we create L left, right? But now, think about this. Let's look at this problem further. Let's look at this problem again. We are given a set of left endpoints in the I meet. Oh, this is I meet, right? This is segment in the I meet, right? This contains all the segment in the I meet, right? So we are consider all the left endpoint of the intervals in the I meet, all the left endpoints, and we are trying to answer if some points fall in this range, right? And this could be arbitrary, like a query, right? This could be arbitrary query as long as this line segment, okay, fall in the left side of x meet, right? Right? So, well, this problem again is very familiar, right? Given a set of points, find the points, return the points in a window. That's range query, right? That's range query, right? So you could store this left endpoints in a range tree and treat this one as a range query. You just return the endpoints, okay, that are inside this rectangle range, right? Okay, so by doing so, okay, instead of storing the list L left V and L right V, we have two range trees. Okay, a range tree T left V on the left endpoints of the segments in the I mid V, and the range tree T right V on the right endpoints of the segments in the I mid V. So all these left endpoints will be in the range tree. All the right endpoints will be stored in another range tree. Okay? And if you do that, then we are able to deal with the original problem, the window query. So the window query, the solution actually, the data structure requires a combination of range tree, interval tree. Okay, we require both of these data structures to work together to solve the problem. Okay, the range tree will be used not only to solve the first two types. The first two types and the part of this overlap boundary. Okay, because some of those, I mean, the endpoint will be still inside this query region. But some of the boundary, this some of the like this, the endpoint is not inside this range. So for all these the cases that this query window include one or two endpoints, we can use range tree to solve that, right? And for the case, when the endpoints do not contain inside the query region, okay, we use the interval tree, but eventually we still need to incorporate the range tree in there, okay, to deal with that, okay. So range tree do it log n squared plus k. Previous I talked about that already. So go back here, okay. Okay, so total amount of storage for the data structure becomes n log n. Why? Originally it's linear, right? Originally it's linear. But now, why it's n log n? Because, okay, we store it in the range tree. If you still remember, in the range tree we use more data, we use more space to exchange for the faster query. If you still remember, and you can check out the discussion in that chapter. The extra storage we pay is roughly like a log n times the original space. So that's why, if originally is n is linear, then we have to multiply the log n to that. So the data structure, okay, storage space complex becomes n log n, and the pre-processing time is still n log n. We need to remember. If you deal with, I think previously when we talk about the range tree, I talk about this, right? The range tree is something like let me write here. The range tree is something like this. So for example, here you sort it according to the x coordinates, but in here you will sort it according to y coordinates, right? So this one, okay, each of these you are sorted using the y coordinates. But if you do this sorting separately, that's too expensive, right? Remember I told you, you just sort it once and you put them there, right? So that's how you deal with the, you are able to create a range tree. With still like n log n preprocessing time. Otherwise, it will be more expensive than n log n. Okay, so there's some small technique we talk about. In the range query chapter. So I just hope that you still remember that technique. Basically, we will sort in this. We actually sort the x coordinate once, and we will sort all the points using the y coordinate again once. Okay, and then we will just put them in the right place. Okay, for every level. So this is like why. Okay, the preprocessing time remains to be n log n. Okay. So the conclusion here, okay, let S be a set of n horizontal segments in a plane. Okay. By the way, so now, okay, so we are able to answer this thing, right? Answer the points in here. So you may ask, so this is not window query, right? So why is it like what's the relationship of the original window query and this one? Okay, let me make it clear. Okay. Say the original window is like this. It's like this. It's like this. This is the original window. Okay? Now, remember, you want to report the segments that the endpoints are not in the window, but the whole segments are in the window, but it happened that the endpoints are not in the window. Right? Right? Where is it? This one. This thing, right? This thing, right? Right? So, what we are doing, the query that we are doing actually is something like this. We use this one. We try to find the endpoint in here, like this one. You know what I'm saying? Okay, same thing, okay? From here, the top one, okay, will contain this one, right? And this one too. Okay, so let's go back to this one. Actually, the window that we are doing is this one. And for the horizontal segments, this endpoints actually will include those segments that go across the whole window, right? Okay, so this is can be used to answer the window query, right? Okay, for the vertical case, we need to basically create another interval tree, okay, and and then this window query becomes like the top one, okay, or bottom one, depending. You can just pick one of them, okay. You don't need to do both. One of them is good enough because we only need to deal with the segment that go across the whole window, right? So it actually will go out of the window on both sides. So you can use left side or right side. Either one will be fine. Either one will help you to identify those particular. This one. This one. Either you use for this segment, either you use the top one or the bottom one. I mean, the top one will find this endpoint, right? The bottom one will find this endpoint. So either one will give you this segment anyway. Okay? So you don't need to do both sides. You just do one side and do this one. That's good enough. Okay? So hopefully that answers the question why this one doesn't look like a window query. Because window query, yeah, I mean, this is like this area is not in the window. This is actually outside the window. Okay, outside the window. Okay. So that has to be a set of n horizontal segments in the plane. The segments intersected a vertical query segment can be reported in big O log n squared plus k time with a data structure that use n log n storage, where k is the number of reported segments. The structure can be built in n log n time. So this one actually include both all the four types. Okay, not only some endpoints in the lie in the window, but also for the case, for both endpoints not included in the window. Basically we're able to deal with all of them. Okay, and you can see that the time complexity is cheaper than linear. Okay, that's important. Otherwise, we would have simply used check every interval. Okay, and then go back to the original problem. That has to be a set of n-axis parallel segments in the plane. Okay, because here we have n horizontal segment. Now we have n-axis parallel segment, which can be broken into some horizontal segments, some vertical segments, and we'll deal with them separately. Dealing with them separately doesn't increase complexity anyway, right? So the segment intersecting x parallel rectangular query window can be reported in big O n log n squared plus k time with a data structure that uses n log n storage, where k is the number of reported segments. The structure can be built in n log n time. So we finally are able to deal with this window query. Okay. Well, yeah, I don't think we have enough time, even though we have 20 minutes. But the next subject is this is like a beginning of another data structure, okay, which is quite it requires a lot of time. But let me at least explain the rationale here, okay, the idea here, okay, at the beginning, and then we will discuss a detail of the data structure later, okay. So the range queries in the window query, okay, here I'm talking about this type of range query. Okay, this is a special range query. Okay, why we call that a special range query? Because, one side of the window is unbounded, right? Okay, in such a range query, one side of window is unbounded, right? Okay, so this is so that's why we call that, okay, a special type of range query. Okay, they are unbounded on one side. Okay, so the idea is that, okay, because this is a special type of range query, because the original range query basically of course original range query includes such case, but the original range query also has a case you have four sides are all the four sides are bounded, right? But in this particular range query, because one side is unbounded. And the thing about this, okay, because of this, okay, so because of we incorporate this range tree here, so that is actually the reason. Okay, the query time becomes log n squared plus k. I mean, log n squared plus k is pretty good. I'm not saying it's. I'm not complaining that much, but think about this. Okay, let me try to. Okay, for the first two cases and part of the fourth case, where some endpoints lie in the window. Okay, we could use the range query to solve that, right? But the range query to solve that actually, okay, actually is log n plus k, right? Log n plus k. So, of course, this one we assume we use fractional cascading. Otherwise, it would have been log n squared plus k. Okay, but at least I'm telling you, okay, there's a way to reduce this query time complexity to log n plus k, right? But when you use the interval tree to deal with the third case and the part of the fourth case, well, you are not able to get a query time better than the log n squared plus k. Okay, that is the reason why in the conclusion, okay, you can see the query time is log n squared plus k. Okay, this log n squared plus k is not caused by the first two cases and part of the fourth case. It's caused by the third case and the part of the fourth one. Okay, it's caused by the combination of the interval tree and the range tree. Okay, and we will, if we are able to find a way to further reduce this time complexity here, then we may be able to reduce this one to log n plus k, right? Okay, so because that one, okay, I mean, in its a range tree part, I mean, it is a special type. So we want to know if there's a, if we can utilize that property to reduce, to get a better performance. For example, we want to reduce the storage complexity to linear. Okay, so so there's like a data structure called a priority search tree. Okay, which gets the idea from the priority queue. Okay, what's that? What's the name for that? What's it? The heap. Yeah, heap. So basically, like, I mean, you guys are familiar with heap, right? So priority search tree is kind of like based on heap. Okay, but it's a much more complicated than that. Okay, so and we don't need for fractional cascading. Then we're able to get a better performance. Okay, so what is this? How do we deal with? How do we like what is a priority search tree and how do we deal with this problem? Because this is like a big discussion. I mean, I don't think, I mean, we just talk about like a little bit is of any help. So I think we will stop here today, okay? And we will discuss like, we'll finish this chapter and maybe talk about a little bit of next chapter next time, okay? Okay, so any question? Uh-huh.
But he also says that the story bound for
No, no. This is for the case, the first two cases and part of the fourth case. Okay, I mean here we are talking about the way to improve the third one and the part of the fourth one. Yeah, you are right in the sense. Yes, there's not. Yeah, we eventually we probably wouldn't gain too much on the complexity of the window query. Okay, but for that particular case, we can still reduce the storage complexity. Okay.
What's the importance on improving this particular? Will it apply to other algorithms?
This is just like let me put it this way. Okay, this is just like give you a motivation to learn a new data structure. Okay, I'm not saying this data structure is going to help that much to the window query. Okay, but I just hope like by discussing the window query. Okay, because this one can also be used for window query. Okay, so it's kind of serving as a motivation to introduce that data structure. Is that okay? Okay, I'm sorry. I mean, it may not help that much in window query. Yeah, I mean, you are right about that. I mean, because in the window query, you need to deal with all four cases. Yeah, but anyway, this is also one of the important data structure. Okay, and we hope to cover that. Okay, but anyway, let's discuss this next time. Okay. So any question other than this one? If no question, let's call it a day. Okay, and we will come back to discuss about this priority search tree next time. Okay.
所以你是说 priority search tree 是很重要的 data structure？
不是，就是这个课会教的其中一个 data structure 啊，我什么叫重要？不是看你定义什么叫重要。等一下，我首先带一下这个，避免。
报告是要用英语的。
对，我忘记讲哦，对，忘记讲这个。Sorry, one very important thing to announce. I keep forgetting that. Okay, we have final presentation. Remember that I mentioned that in the syllabus, right? So I want, because we have still have too many students. I mean, I cannot have like each student to do a report. That's going to take too much time. But can you find like one? Let me see. One classmate to form a group, like
你一开始说3个人一组。
3个人一组，对不对？但是okay, so find 2 classmates. Okay, I mean three because 那我不知道现在班上有几个同学，因为现在有一些人退掉还是什么东西。
我们已经找好了。
已经找好了。Okay. So 3 students to form one group, and please submit this information along with homework 4. Is it too early? Too fast? Homework 4. Yeah. I mean, just find like a teammate. Okay, each team will have 3 students. Huh? 对。看你们都在那边混在一起嘛，所以你们就3个，你们4个。1、2、3、4，尴尬，还有anybody need one additional teammate? Okay, I mean, we'll talk about that. I mean, the report does. I mean, if you can use English, that's great. But it's not required. It's not required because if everybody use English to report, I may not be able to understand your presentation.
Yes.
Okay, but using English for presentation is encouraged. Okay, it's encouraged, but it's not required. Okay. After all, this class is carried out by English, right?
可是有要包括我们要报的那个论文的主题吗？
论文的主题不用，
不用。
但是主题我希望在 homework 5的时候我再问你们。反正我们还有2个 homework。
不过我们有先找啊，如果就到时候有人就他们也找好，然后撞到。
会这么巧吗？你知道这种机会很小的啊。
老师，我找你的论文。
你找我的论文？不要啦，不要用我的论文啦，用别人的啦。对啊，有那么多。
那个是我们今天讨论
的。啊？
我们就稍微讨论一下。
你是找哪一篇？
好像有那个什么，就是好像在附件那个 node 的演算法。
哦 ，deployment 那种东西。
对。
OK。机会不大啦。你是跟谁听在一起？怎么会用我的论文？
我们就随便找，然后就不小心看到。
好。Yeah, I mean, I will ask about the topic of your presentation in the homework 5. Is that okay? Okay, so please find your teammates and report that in the homework 4. In the homework 5, I will ask you the topic. Yes.
要报告。
啊？
要报告什么？
报告一篇 paper 啊。
随便都可以。
跟计算几何有关。Yeah, has to have something about data computational geometry. Okay? Yeah. Okay.
But we doesn't now need to implement follow the paper. We just read the paper and review paper.
Yeah, just prepare a slide and but each team probably only has like maybe 10-15 minutes for the presentation. I will see how many teams do we have. And then decide like the amount of time for each team. So try to be short and to the point for the presentation. Yeah, that's the important thing.
How many minutes?
So I will tell you. Okay, I will first check like how many teams. Basically, it must be more than 3 hours, but I cannot let the presentation just go forever, right? So in the past, like the presentation can run for like more than 4 hours, that day. But yeah, that's. Yeah, I'm sorry. I should have mentioned about this. Much earlier. Okay, I forgot about that. Yeah, but you guys still have enough time to find your teammate and to find the topic, and hopefully, after we cover so many concepts, you have a better way to find like useful papers for your area, because a lot of you are graduate students, right? So you should be able to find like some application of computational geometry in your area. That's the one that I'm looking for the most. Okay? Yeah. I just hope this class can be helpful to your research.
Thank you.
Thank you.
那个 priority search tree 其他一般会用在哪里？